All right, let's get started. So welcome everyone. This is the AI Frontiers Forum, and also this is also hosted by the Bay Area Machine Learning Group. So my name is Junling, and probably those of you who signed up for this talk have seen my bio. I've been working in the AI domain for the last 20 years, most recently building my startup Coach.ai, where we actually implement a large language model to deliver the expert coaching solution. So for today, I'm very interested in give a very short tutorial because it does require much more content in the background. We have about 1.5 hours. I will try my best to get to as much as possible. There are a lot of technical detail in Llama 2. If for those of you who are very interested in more theory or improving, going into the back to understand what is happening, particularly if you want to build a career in AI, whether as a data scientist or as a data engineer. Understanding those architecture will be very important for you to optimize your solutions. Then, but we will leave some time, at least 20 to 25 minutes, to go through the actual code and see the demo in action, so that you will have a confidence that you can actually take the Llama 2 and run it on your own environment or your own notebook. So when we before we get started, many of you, we all heard about the term large language models. Now is essentially almost a synonym to what people used to call AI. That's mainly because ChatGPT becomes so ubiquitous, and everyone think every AI model is a large language model, even though that's not fully true. And in terms of like, in the sense that what's powered behind, whether it's a diffusion model, whether it's robotics or current ChatGPT, we can say nowadays it all transitioned into a transformer-based model. And what is a transformer? Transformer essentially is a deep neural network. We build the neural network into many layers. And the layers inside each layer we have attention, we have feed forward layer, which I want to go into detail. Many of you already learned the transformer. So that is what we have as a fundamental architecture for all today's AI program. On top of that, the language model was basically trained on the text. So this neural network, if we feed a large collection of internet text into this neural network and just do unsupervised learning, the first word predict the next word and the second word predict the third word, doing this unsupervised learning on the neural network, somehow magically it will become very smart. And this is what we call pre-training. So pre-training, we take a large collection of text, just let it train itself without any human label. So all the large language model typically has, it basically is required to have this pre-training phase. And because people discover that pre-training really improve the performance. Without pre-training, there's basically the performance is much worse. And today's language model is much larger than before. Just to give you an idea how much we have come. The first GPT has about 100 million parameters, which is 1/10 of 1 billion, right? And so today, any large language model has to have more than 1 billion parameters. And so I want to use the example of GPT-3 to explain a typical architecture of a large language model. So in the GPT-3, which came in 2020, it is a transformer with only decoder in the transformer. So we talk about a transformer has an encoder and a decoder, two components in the original transformer. but all most recently from GPT and then Palm, then the today's Llama, they all only use decoder side. In the decoder side, there are two major layers: attention and the feed forward layer. And so we so on top of the there's a layer normalization. That is just normalizing the weights. But as you can see here, the order is switched in the GPT model. The layer normalization actually goes before the attention layer. That's just a little bit of architecture change. But fundamentally, what you see is all the large language model essentially is a duplication of a stack on top of each other, the same kind of layers on top many times. So in GPT, you have 96 layers, each inside each layer, you have this sub layers of attention and feed forward. And the embedding can, which is how large vector, the vector size you represent each word. And so it can become very large. So this is the GPT-3 model. The problem we are facing, and as we see that in the past, from GPT from 2018, GPT-2 2019, GPT-3 2020, then goes to Golfer and Palm. Palm is from Google, Golfer is from DeepMind. The model size become larger and larger, so they double each other. Eventually reached like 540 billion in Palm. Then the reason it goes become larger is because they are more powerful. We haven't even reached the limit of the saturation, so we can still make the Palm even larger. However, the major problem we face, and which is the motivation of Llama, is it's great to have a very large model, have very powerful inference. But what if we are in the production? We have to deploy this model. If think about normal GPU, like A100 is 40 gigabytes of RAM. If you have billions, like 540 billion, how many GPU you would require? And it has to run in the inference time. It has to run 24/7. So that's very expensive. So it's not only expensive, it's very slow too. Secondly is in order to decrease the size of a large language model to be reasonable, we do need to have a better performance or even equivalent performance. If it's even though it's smaller, but it doesn't perform well, it doesn't help us. So that's the motivation of Llama. They say, can we reach similar performance as a GPT, but have a much smaller model? That's the motivation. And what's exciting is they achieved that purpose. Now the model for Llama actually started from another model from DeepMind called Chinchilla. So Chinchilla is motivated by Golfer. I mentioned earlier the large model Golfer. Golfer has 280 billion. So if you look at a Golfer, it has 80 layers, has 128 heads. So it's very large. The Chinchilla basically is the idea came out in 2020, 2022. In early 2022, I think it's in March 2022. So they have this idea: what if I can cut down the size to be 1/4 of before? So 1/4 size, half of the heads, the attention heads, half of the model size. So that makes the total parameter only 70 billion instead of 280 billion. With much smaller model, Chinchilla was able to achieve. If you look at the bottom, just look at the performance of Chinchilla for 5-shot performance. It's actually better than Golfer, better than GPT-3. So that's something very surprising. Now, how did they achieve that? Is actually very smart, very interesting. Since they have a much smaller model, the way to achieve better performance is they train much longer. They have and also more training tokens. And golfer has 300 billion training tokens, but the chinchilla has 1.4 trillion. So basically, the conclusion is that if you have a smaller model, but you train, if you have 1/4 the size in the model, then you train 4 times of 4 times the number of tokens, basically 4 times of training time in the training process. That's and then you can achieve even better performance. So this is the major insight of chinchilla, and the Llama essentially is adopting chinchilla's idea. And as you can see, even the number of parameters is similar to chinchilla, 70 billion. So that is what motivates Llama. And what's inside the Llama? Essentially, it's a kind of collection of all the recent results. First, they use a decoder only, which is very similar to GPT-3. Second, they put a normalization layer before the attention layer. It's also like GPT-3. This is different from Palm or BERT, where normalization layer comes after attention layer. Then Llama also adopt another activation function. So remember, we typically use ReLU in deep neural network. We typically use ReLU, or later they use GLU. But SWI-GLU, let me actually explain SWI-GLU. So SWI-GLU is a function combined with a switch function, multiplied by the weights. So basically, you have 2 weights from the input from the previous layer, W and V. So you can make a XW goes into a switch function and multiply by another set of linear transformation. So that is the SWI-GLU activation function. Now the third another uniqueness, which we call uniqueness, but I think it's not that crucial, because the rotary position embedding seems very fancy. So I want to explain what it is. In the original transformer, the position was embedded as an absolute location. And so if you location is T basically represent a number from 1 to a natural the end of a position index. So by the even number and odd number, they transform that into a sine or cosine. And so that basically create a cap on the position embedding value, basically between basically should be the absolute value should be less than 1. Use a sine or cosine, and also create a kind of a cycle inside the position embedding. So that is the idea of absolute position embedding. So you create this relative distance through the sine cosine. The later from 2018, people started to use so-called relative position embedding. Essentially, we are learning about the embedding of the position. So we position our 1, 2, 3, 4. All the integers, then you connect them with weights to the next attention layer. So we are learning the weights for the position. We are learning the weights for the embedding, the word embedding. We are learning both weights. So it becomes a learnable parameter for position. So that's called a relative position embedding. Now with the rotary position embedding, they basically mixed the idea. Essentially introduce this cosine sine transformation on the position, and essentially what the visualization is that if you have a point in the space, you rotate, you turn that to a different location, as long as you can trace how well it rotates, that gives you a relative position. So essentially, that's another way they show that it's still very stable. When I read the original paper, which is published in 2021, the performance improvement is not that significant relative to the relative position embedding. So, for example, the current ChatGPT still uses relative position embedding, and their performance is still very good. So whether the so personally, I think a rotary position embedding is interesting, but not fundamental. Doesn't make a fundamental difference. The real fundamental difference comes down to the training, the training tokens they have. Now, when we here's what's inside the Llama, and the Llama 2 basically follow the similar architecture. So you have 7 billion model, 13 billion, the 32 and the 65 from original Llama. The embedding size gradually increase to double as before. You have number of attention heads, and the number of layers also increase to 80 layers. And you can see with Llama, this Llama's performance, which already got people interested because they actually have better performance than Chinchilla and Palm. And then in the other dataset, the existing dataset, which is also used for open LLM leaderboard, where if you go to Hugging Face, you can see the ranked open source large language model. They use Boo, Q, Hello, Swag, Winograd. Those are all the major dataset. So Llama achieved a relative good performance in all these open dataset. So actually I want to jump to here to what makes Llama 1 perform very well. As you can see that the token size, they reached 1.4 trillion tokens, and then you can see the training loss keep decreasing, and it hasn't saturated. So from just this graph, so Llama 1 came out in February this year. Llama 2 is in July, so only 5 months. 5 months later, the whole motivation, as you can see here, is what if we keep training, because training loss is still decreasing, what if we keep adding more tokens to Llama 1? So in the Llama 2 picture here, as you can see, if you keep training, it still keep decreasing. That means potentially we can have 3 trillion. Right now it's 2 trillion. Potentially you can keep adding more tokens to train. It still hasn't reached the limit yet. It's not flattening. So there's still potential, but it certainly takes a long time to train. That's a lot of computing resource, right? If you look at the paper, it's many all millions GPU hours, more than 1 million GPU hours. Of course, they have thousands of GPUs train at the same time, but it's very expensive to train with such a large number. So this is what we get from having a lot of tokens, and then we can have a very powerful pre-trained model. That is what Llama 2 is. And you can also see it's corresponding to the size of the model. It's 72. The 70 billion is way better than the 34 billion, right? Then the very simple, clear inference, the reasoning from here is why not have a 100 billion model, right? We can even be even better. So there's still potential for the size to increase here, and also the training data to increase. So I want to come back to what is Llama 2, well, the innovation of Llama 2 relative to Llama. What we saw that Llama 2 added more tokens, 40% more tokens from Llama 1. So now it's 2 trillion. Another innovation it used, it's called grouped query attention. We know that in multi-head attention, they basically chop the input sequence into chunks, each chunk corresponding to a attention head, and then you do query key value operation. That's the attention operation. So they are parallel to each other. after that, you concatenate the result together to form a vector that's the same size as your input. So that is the multi-head attention. People been using that all the time. And then later, recently people say this is very expensive. We have to do so many attention operations. Why not just one attention operation on all the segments of the input? So on the right side is called a multi-query attention. So we aggregate all the queries. Basically, we still have corresponding query to every chunk of input, but the key and the value has only one. So this enables much fewer computing because you have to do this attention in every layer. This reduces computing. The problem with this aggregation is your performance will degrade. So that's a dilemma. What people then work on, discover is maybe we can do so-called grouped query. We can group maybe two chunks together, have two query corresponding to one key, one value. So this is a compromise between the multi-head and the multi-query. So that is used in Llama 2 today. And now if we compare Llama 1 and the Llama 2, there are several modifications. One is the grouped query in the center, grouped query attention. Another is the context length. The input length doubled from 2,000 to 4,000. The number of training tokens, as I mentioned earlier, increased from 1.4 trillion to 2 trillion. The learning rate is the same as before, learning rate and the learning schedule. So if you, for those of you who learn the foundations of deep learning, is the learning rate determines how much experience you use for the current update. So when you start with a small learning rate, you take the current, you multiply by the current weight update, and that will add to your new weights. So we allow this learning rate to start with a number and do a warm up. The warm up typically means you allow it to actually increase to a certain number, and then let it decrease. So basically we value the new experience within certain number of period. So the first 100 period, maybe all the new experience give you new information, but after a while the new experience may override what you have learned so far. So we will after warm up period, we will decrease the learning rate gradually until it reach almost to 0. Then you stabilize the learning. So when the learning stabilizes, that's when the training finishes. So that is a learning rate schedule. It is very crucial, certainly very important. That's why every paper talk about their learning rate schedule. Now the training data they use is this public data set. This is what they are very proud of, is because all the other large language model like ChatGPT or Google's model, they all have private data, not accessible to the public. So Facebook or Meta basically very try to approach this from total open source viewpoint, where all the data set, the training data are public data set. So as you can see here, the majority are from Common Crawl, the home web pages, the people been crawling. And then we have GitHub data, Wikipedia data, books, archive articles, and the Stack Exchange messages. So this is all added together. That's the training data. There's one more thing we needed to mention is Llama 2 chat. And this is the indicator because actually Meta is very interested in the conversational model. They have a very good lab working on conversational data before, like the BlendBot group, which we presented in this meetup before. The conversational AI is a crucial part. We know, like myself, for Coach.ai, we want to build a very good conversational model. It's because ChatGPT, even though it's very good in answering questions, it didn't address the issue of conversation. Conversation is way more than just answer a question from a document. It involves empathy, it involves understanding of previous conversation, previous context, also the personal model. So the chat has its unique challenge. So the way Llama 2 trains the chat is basically modeling after ChatGPT, how ChatGPT improves. We two kinds of feedback, right? So essentially three major supervision. Number one is so-called supervised fine-tuning. The supervised fine-tuning is just a fancy term of basically it's basically supervised learning with some additional data. So they take the Llama 2, the pre-trained model we just described. They take the Llama 2 model, then feed more chat data into this model to keep basically let the model continue to learn. Now the continual learning they may use a so-called fine-tuned framework. So there are two ways you can update the original model in the fine-tuning. You can update all the weights, or you can update, you can freeze the previous weights and add some additional weights as adaptation. That's the idea actually for today's Llama fine-tune. All the fine-tune now use this adaptation model instead of update all the weights. So we actually freeze the original model and attach some new weights to the fine-tuning, and then merge those weights into the new model. So that is the supervised fine-tuning. That's number one step. After that, they use reinforcement learning, RLHF, reinforcement learning with human feedback. Now the reinforcement learning, as we know, that the essentially is treating the language model as a decision, as a policy function. So what is a policy function? Policy function in the reinforcement learning methodology is given the state, given the current environment state, what should be my action? So policy basically is essentially is your action is a function of your current state. So here the state is the input for the for the reinforcement learning applied for large language model, the input, the question from user is your state, and your answer is your action. So the answer is what I should say back to the user. So it's a decision I have to make. Every word I choose is a decision. So basically we're learning about the response, and that's my action. Now, the way to improve this model with reinforcement methodology is basically give a reward for what I said earlier, right? So if my response is giving me higher reward, I should use that to keep increasing the corresponding weights. If it doesn't give me higher reward, I should decrease the gradient of those weights. Now, how do I know the reward? How should I, what is the reward? So they, on the upper left is the reward function they are learning. So the reward function basically is using human data to tell, they let the human to write out all possible answer, or let the system also generate answer, but let the human to rate, to give a rating to different answers. From there, they can learn about the reward function. So there is a function they build from this human data. And using this reward function, they can evaluate now our language model as a policy function. They can evaluate the policy function, how well I have said about this question. So that is the human feedback part. There's much more detail, like using certain kind of reinforcement learning method, like PPO they mentioned in this paper. Those are the details we can later dive into. but that is the high level understanding about Llama 2 chat. So what get people excited is just with this small model, 70 billion, and it actually perform in the human evaluation data they got, not certainly in every data set. Is if you look carefully in some college exam data set, they didn't outperform ChatGPT, but in the conversation data set they had with human evaluation, they outperform ChatGPT and the PaLM. And so you can see if you add the win and the tie, 64% of the time they are basically all better than ChatGPT. Then with relative to PaLM, it's 77% times. So this is very impressive performance. Consider their size is like 1/10. Yeah, about close to 1/10 of other model. And that's the number one. The second part is they are open source for commercial use. So that's why people really want to take this in-house to build the application. Many company, financial company or enterprise, they have sensitive data. They don't want to send out to other, through the internet to OpenAI or to other companies. So this could be a solution for them. So that is the Llama 2. Now I want to get into the meat. I think many of you probably are interested in today is how we actually take the Llama 2 to fine tune it. We want to understand. So first, we want to understand how exactly do we fine tune Llama 2. So as I mentioned, I want to actually, I have a slide. The fundamental methodology we are adopting for fine tuning is so-called low rank adaptation. And this is it's a new concept, and that is very important concept, because traditionally when we fine tune BERT or fine tune other model, we change the last layer or we update all the weights. But essentially when the language model gets larger and larger, those are not options. In addition, right now, we are doing generative model. So you don't have to change the last layer. There's no point to change the last layer. So what we need to do is a so-called low rank adaptation. We freeze the previous weights. We don't touch that, but just learn about A and B. That's the weights we're learning. Well, after we finish learning, then we merge these two models, because A takes the input, some input are sent to A, and the process through time, through layers, it reach the B and reach the output. So we learn this additional parameters. Then when we do inference, we add them together. So we merge. You will see in the code, we actually merge them into one model for inference. That is how we do the inference and fine tuning. Fortunately, how do we do fine tuning is Hugging Face wrote a very good package called PEFT, and the PEFT is a parameter efficient fine tuning. They essentially include this low rank algorithm inside the package, so you don't even have to write your own implementation. This is what's nice nowadays. If you want to do anything, people already wrote some open source package and uploaded it to Hugging Face. Another thing we are using today is TRL. TRL stands for Transformer Reinforcement Learning. However, we didn't actually use the reinforcement learning part. We only used its supervised fine-tuning part. So in the so-called reinforcement learning methodology, there's 3 steps. Number 1 is a supervised fine-tuning, where you add additional training data to do just do supervised fine-tuning, like what we showed here in this picture on the lower right. So so that package included this diamond, this purple diamond. Then they also include other package, the PPO, proximal policy optimization. That is the one update the actual language model through the reward. And so that has another package. And the third package is building the reward function. So those we are not using today, but we definitely use the SF, the supervised fine-tuned SFT trainer inside this package. So these are the two important package. They are, if you use Llama 2, you also notice that they also have a implementation, so-called multi-GPU parallel implementation for multi-GPUs. You can choose to use it or not use it. It's really up to you. I think the default, what's nice is default, they can allow you to do multi-GPU parallel to different machines. So that's very nice. For us, we use a very large GPU machine, so we don't have to worry about that. So, okay, so now let me do some demos. First, I want to explain the Llama, how do you actually start with fine-tuning? So there are some steps. There are some steps you have to go through. Let me actually share my whole screen. Maybe that's easier for me to switch windows. Okay, all right. So I'm sharing my whole screen. First, we know that Llama. First, let me open the. Okay, let me open this just so that you can see the Facebook, the GitHub page to get a feel if you want to actually use it. So Llama is hosted under Facebook research, and here they only talk about Llama 2 because the Llama 1 is old. So this is where, so if you want to start fine-tuning, the first step is clone, do a git clone. So you clone this code into your server. After that, you need to go to this URL to get a license. When you go to this page, we can go there now. It's a one-time. So you go there, you fill out this form, required access. When you finish, they will send you email with your link. So it's a long, basically it's a very long string, unique only to you. So that is a link. So when you now, after that, you run this download the SH, you download the actual model. So you can even this git clone give you the code, the basic code, like requirements, download the SH or the script. But the actual model, you have to enter this agreement URL. And so let me show you the download.sh. Okay, so this is the download code. Let me make it larger. Okay, so in this download code basically says it requires you enter the URL. So the first statement is enter the URL from email. You already got approved. After that, it will start to download the model. So the model essentially, these are the parameters, but essentially it's 7B. 7B is the 7 billion model. Llama 2 7B, this is the model pass, and then 7 billion chat. if you want, you can also download the 70B, 70B nature. Those are very large. For today's purpose, I only show the example for the smallest one, 7B. The rest should follow. So you download this model. What do you do after this? Is you here, this is an example. You run this on the command line. So after you download the model to your drive, you run this to build the model. So let's open this example chat simple.py. Okay, I'm going to use my own directory. I think it's not easy to see from here. I'm going to use.
You got to press on the view code.
Hello.
Yeah, press on view code. You see that view code?
Press on what?
View code. If you go down, there's somewhere it says view code. Yeah,
view code. Okay, sorry. Yeah. Okay, all right. So example chat compilation is let's open that. Okay, so what this does is it's actually this is doing inference. The reason is after we download, we want to see whether the model actually works. So this is not fine tuning. This is building it's generating answers. So basically, it has some examples. These are the examples, and then it also allow you to input some answers. So if you run this, it will ask you. Let me see. I have the code. Let me go to my code. All right, so if you run this on Colab, I highly there are many reasons you want to run in Colab. Is Colab, if you run, we have a Colab Pro Plus, $49.99 a month, that give you access to A100, which is a very powerful machine with 40 gigabytes of RAM. If you don't have a Pro Plus, if you're a Pro, you can get access to a 16 GB. It's still possible to run this 7 billion model. Probably you have to do 4-bit, not the 4 size. The reason is the 7 billion model requires about 28, close to 30 billion RAM, 30 billion gigabytes RAM in the 4 size. So that's the minimum you would require, you would need. So here I'm not going to run today, but you can see my code. Is you have a directory where you host your model, so you get into that directory in Google Drive. From there, this is just to facilitate processing, the streaming processing, and then you install all the requirements so that it can run the model. And then after that, in the main function. In the main function, if I run here, it actually give me a box for me to enter sentence, right? So what do I want to run now? Okay, and let's still run it so that you understand how this actually in action. Then we do the fine tuning on this. Okay, so first I'm connecting to my Google Drive. All right, so, and then I'm in Llama 2, so I want to go to Llama folder and just install those package that's required. These are all the required package for this to run. Some package is meant for parallel processing, some for scaling. Okay, so and also you need a sentence piece for the tokenization. So all these packages are required. So now this single statement, this is for inference. So we know we are running this code, the example chat simple, and the chat simple is using the model 7B chat, and so this is a checking point directory, and the tokenizer model I think it's also inside that inside this directory. And then now we use a batch, maximal batch size 4, temperature 0.9, maximal generation length 100. So we only generate 100 tokens. The input token is 1024. Okay, so this is the parameter I specify. The most important part, if you notice, is we use a torch run --n process. So this is a parallel processing function. This is a pre-written by Meta's package that allow you to do this parallel processing. If you only have one, then they run with one GPU. But let's start running this one. So it's initializing the model, initializing the pipeline. It typically takes 2 minutes, at least 2 minutes. If it's faster, sometimes less than 1 minute, but the typical time I experience is from 2 to 5 minutes to just load the model. So sometimes we forgot 7 billion is a very large number because we've been seeing 175 billion or even 1 trillion. But for a normal machine, think about you have billions of parameters to load. It actually takes a long time to load. So this is the part. Just keep in mind that you have to. So we wait a little bit to see the model loads, and then we can do conversation with the model. I see some chat. Let me just take a look. Okay, let me see what are the questions, then we can go back. I would say you need the GPU to do inference simply because you have 7 billion parameters. If you use a CPU, it would be very, very slow. Use Ooga Booga. I haven't used that. I would, yeah, maybe you can share how good that is. I know some people are using it. Then, okay, recording will be shared later. Yeah, you don't need a GPU for inference. So the answer for that. Collab depends on Collab. I'll think about it. If you have a model trained in Collab, is there a way to do inference through API? The depends on how you can if you train the model, you save it to outside the direct folder somewhere directory. Of course, you can use that to do inference through API. So this Collab doesn't impact where you save the model. For example, right now I'm inside this directory, so you can link your directory to this Collab, your Google directory. But if you are running your own server, so today I actually went through SageMaker. On SageMaker is a notebook environment. It's a Jupyter notebook. It can link to your instance, so you can build API for people on your instance through SageMaker. Ideally, personally, I would recommend just run this code in the command line in your instance, right? If you have if you have a machine that runs this code, why it takes so long? It's just 3 minutes. Let's wait 2 more. Sometimes it takes 5 minutes. Let me see. It's not even. Let me see how the resource is used. So as you can see, the system RAM is loading 11 gigabytes. GPU RAM has not. So this is what's interesting. If you observe, they first load the memory into CPU RAM. So this will go up from 12 until reach close to 30 gigabytes. So it's loading. Once it is loading to CPU RAM, then it transfer that into GPU RAM. So then after that, after it reaches 30, basically the whole model, it will this will decrease, this will increase. So this is our disk size. Our GPU has not been utilized yet, so they're still working on the CPU. This is very, very slow. With this speed, it will take forever. Let me, this is too slow. Let me stop this, see if I can rerun this command. It's already full, yeah. Would that increase the speed? It shouldn't take, then this will take another 5 minutes. Yeah. So I think if I stop, it may be faster. Let me just stop it. Okay, and load again. So you can see this RAM increase. Now it's faster. See, now it's already 8. Now 16. Yeah, that's good. I made the right decision. And then now you can see GPU RAM is 30. So, okay, so in 23 seconds, now I'm going to close this one. In 23 seconds, so now it's interactive. So I say, hello, how are you? So this is a chat model, which we have not fine-tuned, but I want to just show you the inference, how to use Llama 2. This is how you run Llama 2 on your notebook. Yeah, so, and then says what can I see in Paris? They trained this on a personal assistant for customer support. So they have very good answers for those kind of questions. And let me see, I feel stressed. What do I do? Yeah, very good answer, right? You see it comes back very reasonable, almost like a ChatGPT. Okay, I'm going to stop. So that gives you a flavor of interactive loading of Llama 2. Now I'm going to talk about fine-tuning. So after you have the model, the first step for fine-tuning is convert. So right now it's a pure original Facebook format model. We didn't do any transformation, right? So in order to do fine-tuning, and all the fine-tuning solution I found is you first transform this model into a Hugging Face format. Then we can use a Hugging Face function to interact with our model, because Hugging Face wrote many good functions to work with the model weights and the merge model. So, but they have a very specific requirement on how to represent the weights. So that's the first step. We do the model transformation. I think I wrote some notes here. Yeah. So what you do, the first step is you clone the Hugging Face, and you run this function, convert Llama weights to href.py. I can show you. Let's go here. Let's go here. I'll show you the code to very quickly to see Hugging Face the code is the Llama here. There should be a Llama. Where's Llama?
Hey, Junling.
Yeah.
The Hugging Face repos also have the Llama 2 models in Hugging Face format directly, right? Wouldn't they work?
Do they?
Yeah, they have. I don't think they have 33, but they have the rest of them. I'll just post the link.
Okay, I didn't know that. So we
Yeah,
did a
you can.
transformation. I run this code on the Facebook model I downloaded. So I basically did this step. Let me actually go back to my. I'll show you, see if I can find my Hugging Face transformation code. It's too much work to find. Yeah, anyway, you just assume you have to do that transformation. So now I want to show you the organization of the model. So originally all the Facebook model is saved the 2B chat and the 7B. This is the model. Then let's see, open this up. Yeah, so this is the model. I'll close this one. The Hugging Face under transformers. This is a transformer Git. Yeah, this is a transformer GitHub repo of Hugging Face transformer. But the model I saved, I think is under model. Under Llama, sorry. Okay. Oh no, this is Llama model. Okay. Oh, on the model HF. Okay, here. So I saved all the transformed model in here. The 7B is corresponding to basically is Hugging Face format of the 7 billion Llama 2. 7BF is the Hugging Face format. And you can see here the size of the model. Okay. You see this one, there are two parts. One is a 9 gig, another is 3 gig. So these two, when they use it, they have to merge these two. They basically will load these two together as one model. The reason for that, now let's take a look at 7 billion, okay? So this is the original Llama 2 model in the Hugging Face format, also 9 and 3. The chat is the same size, mainly because it's just a small adaptation from the 7 billion model. So you can see 3.26, 9.29. Let's see how large this is. This is almost identical. So this is the 7 chat model. So now let's do fine tuning. Fine tuning, how do we do fine tuning? Basically, we introduce training data. We pipe in our own training data so that we can update this model, right, into our own model, because that new model will capture the information about our new training data. So that's the whole step of fine tuning. So let me show you Hugging Face fine tuning. So this is the step for fine tuning. Fine tuning, I start with, I think I have too many notebook open. Wait, I think that will consume a lot of resource. So I have to close this one, Okay, now I have this one open. Along. And I mentioned that there are some packages you have to download. I mentioned the path, the parameter efficient fine-tuning package that uses LoRa, the low rank adapter. So this is an important one. The transformer reinforcement learning, this is another package. Bits and bytes, I think it's also using the 4-bit, allow you to do the smaller. And so these are the 4 major packages you have to download. And there are some additional package inside here. Another package you have to download, even though it's not used. This is for visualization, but somehow it's written inside all the Hugging Face utility function and make it easier for you to visualize. If you don't download, they will complain. So I'm going to download this one. So my first step is I'm going to take a data set that's available in the public. I want to just show you the fine-tuning process. Then we can, if we have time, I'm going to show you additional internal data set we use. So here, the fine-tuning is also very simple command, just this, right? But the meat is inside this Python function. I'm going to explain later. I'm going to explain what's inside of this function. So you take this function, you load the current Hugging Face formatted model, the chat model, then say the BF16, the floating point representation is true. Then you do a merge and push. Basically, when you finish fine-tuning, you will load, you will merge the model, the adapter, and the original model together for your inference. This is mainly for inference. And here, if you specify this as true, this is going to use a 4-bit, use only 1/4 of the size. But here I didn't specify as true, so we are actually using the 4 size. The output directory is the name you select. So that is the simple command to do fine-tuning. But first, let's take a look at this function. This is where you actually do fine-tuning. The major functions defined here. So did I call this function? Double check. Let me just confirm. All right. So I actually used this function. This demo is for internal data. So this is a public data set. Let me open. All right. So this is the fine-tuning code. What it does is these are the typing, just the Python function for the types. And you have 2 special data class data sets to load this is the interface with Hugging Face data set. And then in the transformer, we use this. Later you can use it. They have now Llama causal model, causal LM. It's similar to this function. And the tokenizer. So these are the 2 major functions for model and the tokenizer. The rest is just the assistant function, like this is for bits, the bytes. This is for arguments. For example, we have many arguments, many potential parameters you can tune. So far, the default, like many default, we have some default parameter like learning rate, weight decay, those are, and then LoRa is the low rank. So in the low rank model, the adaptation, there are some parameter you can give. like the alpha dropout, the learning rate. This is because you are learning by itself, right? So they are more like a deep neural network by itself. So you give them some parameters. And then you decide whether to do 4-bit or not, right? So what kind of 4-bit? There are two kinds of 4-bit representation. There's one is there's here there's this is the training part. This is different. So 4-bit is represented here. Then you decide number of epochs and the max number of parameters, optimizers, use RWW, all those basic. So there are a lot of parameters. This you can get this code from Llama recipe online. So this is not my code. This is you can get on the internet. Then after that, you use this Hugging Face utility function to process the arguments. So basically, you take this is more like a dictionary. So you have this assign certain values. So Hugging Face allow you to pass into data class. And then we build a model. So the this is just So I'm going to skip the bits 4-bit part. So we are building a model. Basically, we're loading from pre-trained model. The pre-trained is the original 7-bit chat model. From there, you we are going to do a LoRa, the low rank adaptation on top of this model. So this is the pre-trained model and the pre-trained tokenizer. So we return this. So this is for preparing the model based on the current parameter. And then we also define certain arguments. All these are the parameters, basically taking the value from the previous the assignment we get. It's the same, it's all arguments. So here we have the pre-trained model and tokenizer. And before doing that, we need to load our training data, the fine-tune data. So here I have a fine-tune data loaded from the arguments data set name. That's the data set I'm going to use. And I'm also only use the first 20 data points. I'm not using too many because it will take a long time. So this is just for demo purpose. If you have like 100, 200, you can certainly use it. So essentially, you return a type called a data set. And then you can start training. So so-called fine-tuning essentially is training. But the training with this package, PEFT. The PEFT is the low-ranking. So if you specify this configuration, you get this low-ranking adapter. So the meat of fine-tune NARA is essentially here. That's the meat. If you carefully read this 4 statement, actually only 3 statements, then you would understand how this whole thing works. Yeah, actually only 2 statements, sorry. This doesn't allow me to. This is actually 1 statement, sorry, this whole thing. So essentially you define a trainer. The trainer takes in a certain parameter, and the most important parameter is the perf config. That is the one you actually configured to give you a way to do the low rank adaptation for very large language model. So that's the core part. And then you just do the so then you train. You call the trainer.train. So that builds your fine-tune model. Notice that we already loaded the data set. So data set is already sent in here. The fine-tuned data is sent through the arguments. So so in this simple function SFT stands for supervised fine-tuning trainer. in this simple function, you load the pre-trained model, fine-tune the data set, and the LoRa configuration, basically for the low ranking adaptation. So these three major components enable you to fine-tune this model. And this SFT trainer is a subset of TRL. I mentioned earlier, this package, TRL, the Transformer Reinforcement Learning package. So that is the core part of fine-tuning for large language model. I think now if you can see these three, I think everything else is same as the previous machine learning training. The only new part is this three statement. One is you have a supervised fine-tuning trainer. Another is you have a LoRa configuration. And I'm not sure you even use this. Let me see if we actually use this one. Oh yeah, we use this. We use this for inference. We use this after we fine-tune. We actually do a merge and push. So this is inference on a fine-tuned model. So that's all you need, because your fine-tuned model is defined by a low rank. It's adaptation on top of original weights. So you do need the same package to load your adapter in order to interpret as a complete model. So that's the. So the first is for fine-tuning. The second is for inference. That's all you need. All right. So I don't think we have time, but let me see. I will try my best. I want to run. This will take another 5 minutes to run, but you got the idea. Is you load this model, you give your training data. The training data is actually inside this function. You can potentially put in the argument in the command line, but I've already put it inside here. So that will allow you to fine-tune based on a data set. Now, what if I use a different data set? Remember, I use the remember here I use the Hugging Face data set. So it's a public data set, very easy to load. I just call a Hugging Face directory. But what if I have my own data set not available to the public? So I want to show you how to do that. Yeah, so it's here. So here, see, I have a data set here. So I'm using a Panda reading from CSV file. So I have you basically convert a Panda data frame into this dataset class. Once you do that, you can use identical fine-tuning function as before. So that's the only difference. So if you have internal data set, you just load into data frame and then you convert into data set. And the rest is the same. You see the trains the same. Yeah, you see I'm getting the data set here. I'm doing the fine-tuning. Then and then I do the inference. Inference is identical as before. And you do notice that the fine-tuned model saved in the final checkpoint, but the inference is a merged checkpoint. So the reason is I'll show you in the directory in the actual code. So I saved my result in the demo. Right now using this, you can see the inside the checkpoints, they saved this adapter model. This is the LoRa adaptation on top of original model. So this is 128 megabytes. But if I needed to do inference, I will get the original model. So here, I get the original model. So these two already incorporated my adapter. So if I add adapter to the original 7B, it come into this directory to merge the checkpoint. So that's will be my inference. And yeah, I think that covers. So this is for doing your internal data set. Let me see if there's anything else I want to share. The inference. Notice that how do we do inference? I didn't explain to you on the inference. So you use the previous function to load the merge and the push. After you load it, you actually use Llama tokenizer, Llama cost to do the inference. So the inference is this code. The inference is you have to write how to generate the output part. Yeah, just this also from their public code. All right, I think I'm covered most. I want to tell you something more for today's talk. I'm offering, for those of you who are interested, I'm offering a coaching program. So if you are interested in learning more, particularly I know that many people don't have a large language model background, and there are a lot of nuts and bolts. You can potentially certainly enroll in the online class, but if you need personalized help, I'm here. Because a lot of people tell me they need some more personal solutions. So so my coaching program basically allow you to create a roadmap to how you should close that gap. Where's the gap? And if you are consider career transition from engineer to other careers, that's also possible. If you're doing product development, I can also help you to find all the tools and the code, where to find them, how to put a pipeline together. What we do is we do a weekly call, so that it's a very small group. Everyone has questions, you will get answered. Then you can talk to each other. Essentially, you will be in a community of all the other people who are building the AI large language model. Then you can also ask me question every day through email. So this is what I want to offer. If you are interested, you can just go to this URL to apply. And we can then chat to see whether it's a good fit or not. All right, so that's what I want to talk about. Any question? We have a few more minutes.
Did you create your own data set for fine tuning the training?
Yes, it's a CSV file.
Can you show a few examples of that data set? I mean,
it's very simple. It's the example essentially is a question and answer. So it's like a chatbot. The question says, I feel is from our coach. Oh, by the way, I want to show you everyone our company website. So where we gathered so what do we build? The product, you can see the product we built. So in here, if you come here, and we have a different coach, right? We have a famous coach. We also have this emotion coach, Dara, you can talk to. This is emotion. I want to show you what's very cool we built is a video component. So we have Tony Robbins, and you says, you ask, what's the secret of success? And what you are going to see is not only text, we also have video search. So you can right. So as you can see, we have generative answers. We also tied to the person's history, the answer. So we have personalized answer. There's several components in this product we're building. One is we do have an internal document to indicate what is Tony Robbins' article, his articles, his writings, his philosophy. So his answer will be very different. If you ask the same question to another coach here, the answer will be very different. So he has special answers. The number one, so if you have internal documents like HR document or corporate document, that's a separate program you can load into here. And secondly, I don't want to emphasize too much on the video search, but the data also requires transcription, understanding the speech. That's a different component. If you ignore the video part, just the text, you need a pipeline. So the pipeline is how do you build the embedding? How do you save the embedding? Do you need a vector database? Do you and how basically from beginning to the end, right? And then how do you generate the answer back? That is the whole pipeline. So that's what our company has done. Yeah. Okay. Other question. And the data set. So the data set is you can see the typical questions. You can those are the data set. Let's come back here. All right. Any other question?
Hey, I access the link. It points to a Facebook group.
Facebook group?
Yeah.
For what?
For like a coaching group.
Oh, this. So how do we build a community here?
Yeah.
You're asking. I'm planning to use the Slack, but
no, I'm sorry. No, the link, the bit.ly link. When I posted this link, put this in the web browser, it leads me to a Facebook group.
That's wrong. Let me go to. I thought I have the right link.
I had the same issue. So if you capitalize it right, it'll be the right form, I think.
Oh.
So
Yeah. You have to do. It's a capital sensitive.
It's still the same for me.
Let's see. I come here. You see. I copy pasted.
Okay, can you paste this in the channel?
Sure.
In the chat.
Yeah. Copy paste into chat.
Yeah, it keeps getting me to the. Oh,
Yeah.
here we go. Yeah, well, accessing your link seems to work, but.
yeah, I think it's A and I are being capital. I had the same issue.
Okay. Well, I tried the AI cap, but maybe it's the HTTPS.
Yeah, maybe HTTPS. All right, other question?
Yeah, Junling, can you talk about the key differences of SFT versus just prompt engineering, right? Because you can basically ask the model, give it sample question answers, and ask it to respond. Is the SFT more permanent way of?
Yes. So prompt engineering, you have to figure out what's the best prompt, right? And it may change each time. And fine-tuning will give you an updated model. So it's like a permanent memory. For example, if I have a Steve Jobs speech, and if I ask some question that appeared in 3 different locations of Steve Jobs concept, can they aggregate those information into one coherent answer? If I do the retrieval method, like a prompt-based retrieval method, instead of fine-tuning, basically I retrieve the 3 segments as sorted, like the most relevant, and then add a prompt on top of that. It may not understand the 3 components, the 3 segments are connected. So if you have a complex question that involves multiple documents, you won't be able to get those answers. Instead, if you feed those documents into the fine-tuning, your model will permanently adjust the weights and remember the connection between those documents. So the advantage of having fine-tuning is allow you to be smarter on all the documents, their internal relationship. Yeah.
Okay, and just a quick follow-up on this is you talked about reinforcement learning, human feedback, and SFT is a key pre-step for it.
That's right.
Can you talk about the rationale in this sequence? Why we need? I guess it acclimate the model to the domain that you're trying to do your tuning and reinforcement learning, right?
Personally, by reading several papers in the last few months, what we came to conclusion is fine-tuning, supervised fine-tuning is sufficient. We don't need the reinforcement learning step. So if you look at the Llama, Llama is also from Facebook. They didn't use the reinforcement learning step. Alpaca, they didn't use the user instruction learning. Even Dolly, I don't think Dolly uses reinforcement learning either. So reinforcement learning is very fancy, very expensive, because you need to figure out, you need to build a reward function, you need to get a human to evaluate. It's very expensive. So that's why I think the trend, and people already proved that without a reinforcement learning step, just this supervised fine-tuning is sufficient.
But GTP4 uses that heavily, right?
Yeah, but it's arguable how much is from the supervised fine-tuning, how much is from the reinforcement learning step. Maybe for safety, for certain kind of answer, like they are offensive, certain kind of things, maybe they use human feedback for that purpose.
Awesome.
Yeah.
Hey, Junling, one question about fine-tuning. So when you create like a chat model out of a base model, you are kind of typically fine-tuning it with some dialogues, right? So you take the basic GPT model and you essentially tune it with a dialogue, like question answer, and now you get a chat model. And now we are actually potentially tuning a fine-tuned model further for your domain's specific Q&A, right? Has any research been done how a fine-tuning of a fine-tuned model works, and can you kind of keep doing it to make it more specialized, or do you kind of start running out of juice pretty quickly?
I think what we showed that with fine-tuning definitely becomes better, much better.
But you can fine-tune a fine-tuned model and it gets better in that specific domain?
Yeah. So actually the current 7B chat is a fine-tuned model.